So we're going to just kind of put together a 2-day sort of goal of understanding constant proportionality with a graph, a chart, with an equation and what it means and how to use it. And so when Emma was talking about unit rate, she thinks of like a ratio table and there has to be a 1 in it. That's the most common way. So I think that's a great way to think of it. It's when we talk about rate, we're comparing, so it's comparison. Basically a comparison of two measures where one of the measures is 1. So, so just to clarify the word measures, reminds us to use units, so the unit rate is meaningful, like miles per gallon is really different than dollars per hour. So if we just have 15 per 1 and we don't know what it's about, it's not meaningful. So we want to make sure we have the units. And then the constant proportionality, we're not going to worry about that yet, because it's not meaningful yet until we look at some of the other stuff here. Okay, but like with this problem, Fresh Foods has oranges on sale at 10 oranges for $2. So Elliot, what is a rate that you can make with that?
10 oranges for $2.
Yep. I mean, that's actually just the rate. That's one rate. 10 oranges. Is there another one? And you could use a slash. What else? Anything else?
Money for 1 orange?
Yeah, exactly. Or, does anybody have that one right? Did you? Does anybody figure out how much it costs for 1 orange? 20 cents, yeah. And if you didn't, just think about like dollars per orange, just going back to that ratio table. It's just like Elliot was saying, you get $2 for 10 oranges, but if I want 1 orange, the cost for 1 orange, I'm going to divide by 10, which makes my decimal move in, and then money we put 2 digits, it's 20 cents per orange. So 20 cents per orange. So the unit rate has, I made here a unit rate, so I'm going to slide this one down here. And the one that I think Elliot was saying, you could also say $2 for 10 oranges. So a rate just compares two measures, and the unit rate makes sure there's one of the measures in 1. So what's the unit rate per dollar? Would that be, Scarlett? Yeah. So the unit rate here is 5 oranges per $1. So we kind of have two different things. Okay? Thumbs up or thumbs down? Okay. So you filled the chart out. I bet in this room there's 2 different ways to fill the chart out. If I'm going to just use a little color here to focus on this unit rate, we can talk about independent variables. So like if I look at 20 cents an orange and I want to know how much money I'm going to spend, I need to know how many oranges I am buying to figure out my cost. So in this unit rate, the orange becomes like the independent variable. For me to see how much it's going to cost, if I use this unit rate here, I have to say, well, how many oranges am I going to buy? So in that case, I would make my variable, like I could call it N, which is the number of oranges. But then my other variable would be like C, or cost in dollars. So for example, this would be 0.20. Raise your hand if you did it that way. Did anybody start with 20 cents? Okay. So, really? But not ever, did anybody start something different? Huh. Okay. So, if I clone the page here, so now I have, if I take just a different color so you can keep track of my pages here, if I think of it this way, 5 oranges per dollar, if I'm gonna know how many oranges I'm gonna get, I need to know how much money I have.
So you put the money on top.
So you put the money on top, right? So this would be cost on top. But they're both correct. So cost in dollars, because now the dollars, if you have like $10, you know how many oranges you can get. Because you know for every $1, you can get 5 oranges. So that the per one, that's usually more commonly your independent variable. And so then this would be n, which is the number of oranges. Did anybody get that one? One person. It's true. It was less common in the other class too. Don't erase your work because it's probably
I have 2 different sheets with 2 different things.
excellent. And actually the truth is, so do I. But you guys, I only gave you one sheet. So today we're gonna just focus on the one that most people did. This one. Palmer.
So you actually did the one where oranges was on top and glass was on the bottom with us yesterday.
Oh, I started this one in this class yesterday? That's why. So then let's finish it and then you guys, we can just talk about the other one together. Okay, so when you get to 27, so let's pause this and we'll finish. So with the table,
This fruit,
yeah,
how is it 210? When you're
2. I just was brushing. $2, thank you. So tell me what your equation was, Tyler. Can you like make a cost equation? Cost equals, if my variable is n, right here, you see my variable? What would cost be equal to? Yeah, 0.20. I need another variable. Yeah, times the number of oranges, so we could just put an n. And then up here, when it asks you to circle the constant of proportionality, that number that comes in front of the letter n is your constant of proportionality. It's the change that keeps happening, the same change. Like every time you get another orange, you pay 20 cents. So the constant of proportionality in this equation would be every time you get another dollar, you can get what? You get an extra dollar, you get, for every dollar extra, you get 5 oranges. So the constant of proportionality is the other number in the unit rate. But in the chart, it shows up kind of in an interesting way. So this goes up by 0.2. What does this go up by? 0.2. And this is 1 and 1. What about here? 1 and... Okay, but what about here? It's not 0.2 anymore. But what about here? 6. The word constant means the same. These should be the same. So when you look at this, you're saying if you get 1 more orange, it's only going to cost 20 cents. What happens if I get 6 more oranges?
$1.
Right, and what's $1.20 divided by 6? 20 cents. 20 cents. So the constant of proportionality should be the same whenever you take these two numbers and divide them. Like how far apart are these? 340, right? How many oranges? 17. How many times does 17 go to 34? 2, right? So it's at $3.40. It's going to be still, this is still,
Can you explain that?
yeah. So you see if I divide this, I still get 20 cents.
Yeah, isn't that what you were asking?
Yeah, I said 34 divided by 17.
Oh.
You already had done 340 divided by 17. So the constant of proportionality shows up in the chart. So if you were just given a chart and no equation, and no story, and no graph, you should be able to figure out the constant of proportionality after you get practicing with this. We're here. So Rhea, you're making a funny face. You get that?
Yeah, I get that.
Okay, so the equation comes from, well, it's kind of from finding that number. It's kind of from finding, like, there's different ways, but one is if you find this number here, that change for one, it's your number in the unit rate. Because for every new orange, you have to pay 20 cents. So that happens, that's constant. No matter what, if you get an orange, you pay 20 cents. That's why it's constant. It's the same amount of money for every new orange. Does that make sense? So, like, in the graph, it shows up a different way. So make the graph, okay, and we'll talk about scaling. When you make a graph, if it's linear, you really don't need to plot all the points. It's good to check them, but probably it's also good just to plot some of them. Like, you know, I'm going to take a blue line here. If I don't buy oranges, I don't spend money. And if I go through those 3 points, I should go through that point. And if I start here, I could even extend my line longer. And I can check the 27 if I wanted to. I could.
Oh.
I can project where the 27 was. Does that make sense, Katie? So I'm not saying to do that yet. We'll do that in a minute. But the 27 we can figure out. That's why you don't need it, because it's linear. Because look, I only used 4 points. And I recommend that you check. That's kind of what I would recommend, is you use about 4 points if you have 4 points. And then I would go back to your table and make sure the other ones make sense. You know? So, like, for example, if I bought 5 oranges, it's going to cost me $1. That should check out right here. And it does. You see that? You don't need to put dots on every single place.
Because it's pretty.
Because it's harder to read, it's just a lot of stuff. Now look at, what are some of the characteristics, you guys? We already talked about one. What is it? It's linear. What else? Well, linear means a line, and a line is already straight. So linear.
Pattern.
Well, it's steady, so it's linear.
It has to start at the origin.
Okay, it starts at the origin, so that's kind of, it's true. So we're looking for something more general, like it's a diagonal line, and is it increasing or decreasing?
Oh, it's increasing.
It's increasing. So that would be a characteristic. All the other things you guys are saying are true, but this would be something we would look at later. So the more oranges you get, the more money you pay. Okay, so those are kind of characteristics. And steady. So you said steady. That's important. Steady. And the fact that it starts at 0 is also a good observation, because sometimes graphs start a little bit higher, and that becomes more meaningful. That means you have to pay, like, even before you get any oranges. Like, that would mean you would have to pay to get into the store or something. Like, actually, like Costco. You actually buy a membership before you buy anything. That kind of graph would start a little higher. So starting at 0 is a great observation. Okay? Right. So this is what I want to show you guys. Down here, Tyler made the equation cost is equal to 20 cents times the number of oranges. And the constant of proportionality we already talked about showed up as the coefficient. That's called the coefficient. That's a big word, you learned it last year. It just means a number before a variable. And in the table, you guys can put in your own words how the constant of proportionality shows up. in the table, but it's like the way I think of it is it's the difference of the independent variable of the dependent variable divided by the difference of the independent variable. You know, like if you take a difference here and divide it by that number, you get the constant of proportionality. Like these are $3.40 apart. If I divide it by 17, I get the constant of proportionality. That's kind of like a big information. But the graph is much nicer to see. So I want you guys to start at 5 and go up $1. 20, 40, 60, 80, $1. What's the horizontal represent? What do those 5 squares represent? Does it represent money? Right. How many oranges? This is $1. How many oranges does this segment represent? Yeah. 5, right? What's $1 broken into 5 parts? Yeah. So the constant of proportionality on the graph, if you look at those little triangles, you always should get 20 when you divide the up vertical number by the horizontal. So like if you get that? Don't erase your graph, but let me erase mine. Like, what if I did $1.60? 20, 40, 60, 80, 100. So that's $1. 20, 40, 60. That's $1.60. Now I go over 1, 2, 3, 4, 5, 6, 7, 8 oranges. What's $1.60 broken into 8? 20 cents. That triangle is always going to give you like your constant of proportionality. What if I had an itty bitty little triangle? Up 20 cents over 20 cents over one orange. Still 20 cents. What if I just went up 20, 40, 60 cents divided into 3 oranges? I still get 20 cents, okay? So the graph shows the constant of proportionality using a right triangle. That's a good kind of stopping point for this.
That's